Hi everyone, my name is Kyle. I'm in the ALCF, Assistant Computational Scientist. I'll try to keep it high level and brief here. I know it's been a long 2 weeks. I hope it's been good. I myself did it in 2017, so I know by the end everyone can be quite exhausted. And this set of notebooks, or scripts rather, and modules are definitely intended for you to get your hands dirty and try it out when you have time, maybe a bit more space to think about these things and play around with the different parameters and tools. So I encourage everyone to try it out after getting a high level overview here. So just like the last module, we'll work on Theta GPU since we need some of the fanciest, newest GPUs from NVIDIA beyond what is offered for free from Google Colab. And we'll do
Kyle,
everything.
I'm sorry to interrupt. Your audio's a bit low and kind of choppy.
How about now?
Um, Volume's better, and you're still cutting out.
Huh. 1 second. How's this?
Much better. Do you
Okay.
um, just talk a sentence so I can hear?
Testing. This is ATPESC week 2, Friday, August 13th.
Okay, mostly okay. Maybe we should start again?
Okay. For now with the audio issues, and I was going to give a high-level overview of some tools you can use to profile TensorFlow code specifically on the Theta GPU machine and the A100 GPUs from NVIDIA. Like the last tutorial, I was saying everything will be on Theta GPU, but unlike the last tutorial, we will only need one GPU for our exercises. The set of tools you would use to profile distributed training are a bit different than the ones you are going to use in this tutorial to profile single GPU training, single device usage. So I think some instructions are being put in the chat to somehow share the nodes so you can, because there's 8 GPUs per node on Theta GPU, and you'll only need one for this exercise. So I am currently in my home directory on an allocation, which I got by a similar command. I think you'll have to modify this allocation name since you're not an instructor, but everything else should be similar. Again, look at the chat for information. You've done this in the past in the last one if you were following along. And I'll be following along the GitHub, more or less, so you can try it out, and if you get lost, just refer to those documents. So now that I'm on the GPU, I want to get a common set environment with TensorFlow and all the other things we'll need for this tutorial. So I'll use, unlike the last tutorial, I'll use a singularity container. Got this nice long command already saved in my history, which basically launches a container from this image that everyone should have access to in the shared directory that was released by NVIDIA in July, so last month, with a very recent version of TensorFlow. The other options here are, this means use the GPU or expose the GPU to the container, and this means to mount the Lustre file system into the container, which is normally an isolated area of execution. So I'll launch that. So I have this nice isolated container with hopefully everything I need and the GPUs that I start with. Since I pulled an entire node to myself, what I like to do for this type of single GPU profiling is set CUDA visible devices to just a single index, because otherwise TensorFlow will see every GPU and spit out a bunch of extra information at the beginning of every run. Okay, so I'm going to go to the directory where I cloned the GitHub from today, specifically to the final module. And we've got the scripts in here that are very similar to the ones we've been seeing throughout today. and very similar to the ones from the last tutorial and from Bethany's final example of a convolutional neural network. Is the only architecture we're going to be considering today. We're considering in this next 20 minutes. So get open my editor inside the container. So I'll just go to a different window in the same directory. And here I'll give you a little tour. It's set up much like the last one. So Horvath is in fact still in here, even though we won't be using it. There's a logger. Here's the core of the network, which is the definition as we've seen before: 2 convolutional layers, some max pooling, some dropout for regularization to prevent overfitting, and some fully connected layers to do our classification. Nothing's changed here. Computer loss in a separate function. Here's a helper function I've written that encapsulates the loading of the data set that you've seen before. Again, these are 28 by 28 pixel images of single digits, and it's grayscale, so there's only one channel. There's a function that'll fetch a single batch from it, and then here's where all the fun stuff happens. I can't recall if there was a training loop function specifically in the last tutorial, but here you can see the forward pass occurs right here specifically, where we take in the given batch of inputs and make a prediction. And then the backwards pass happens over the next few lines where we compute a loss. It's still part of the forward pass. And then we can do the backward pass for the next couple lines where we compute the gradients and apply the gradients. So always just start with profiling your codes and putting some simple timings in here and logging them, with your loss, etc. And that's everything. Oh, I also put some helper command line options so you can change the batch size and number of epochs and the learning rate from the command line. So let's run this basic one that's unoptimized and, like I said, similar to the ones we've seen in the past. Oh, this is the thing. Always remember to go back to your Singularity container, because there I was operating on a head node. Okay, and we see it training. So here's the logger output. It first tells you the epoch ID and then the step ID, the loss at that current step, how long each step is taking in seconds, and then finally what we care about for the rest of the tutorial, we're going to try to increase this throughput from this kind of minuscule 250 images a second to almost 1 million images a second. 250 might not seem so bad, and it isn't bad in a lot of applications with larger images, but these are extremely small images, especially with only one channel. So just know from experience that it should be much faster. So we are going to start with profiling, as you've probably seen earlier in these last 2 weeks in other settings. We're going to start high level and then drill down into specific functions and kernels to find the hotspots. So a good tool for doing that, getting a high-level summary, is one that's generic to all Python, called the line profiler. Unfortunately, it's not in the standard library, so you might need to install it. It might not be included inside the image distributed here. So a quick way to do that is to install --user, because you don't have writable permissions. You can install the line profiler, so this will put it in your home directory. I've already done this. And what I've done to the file you just saw, copy of it in this folder. Again, I'll have to keep swapping between the 2 windows. Only changed a few things, which is I've added this function decorator, which if you're not familiar with function decorators in Python, it's basically like a meta function that you wrap a function with, which here in this context, profile will link into that library and tell the library to specifically profile this function. And here's the calling function, which I also want to see that level too. I think I put it somewhere else. So 3 places. So in order to actually run this, you can't just execute it directly. You have to use this wrapper. Just prefix it with current-prof-l. I'm going to limit it to 1 epoch because it's slow. In fact, I'll probably kill it before we even get that far. Oop, jumped ahead there. That's the optimized one. Okay, there's the 250 images a second that we were seeing before. We'll let this run for a handful of steps. At this batch size, it would probably take too long to even run a full epoch. So I'll Control-C it, and it says it's writing the profile results to this binary file, which you can then process with okay, and it just dumps out a plain text summary in the time, the breakdown of where your time spent in the various Python functions. Like I said, it's completely generic, so you can use it for any Python code. So at the highest level, with the train network function we have, see that 95% of our time spent in the training loop, which is a good sign. You know, there's 5% spent in just setting up the model, which that would even go down if you let the training run for longer, of course, and there's not much we can do about this. And we don't really care about optimizing this type of one-time cost. So then going into the lower function, scroll up here. This is the main training loop I highlighted. So we see that 96% of the time spent in the forward pass. Now, anyone who's spent any time with neural networks would probably, this would stand out immediately. Because compared to the backward pass steps, it's so much bigger and indicates something's wrong. Because I would say 90% of cases, the backward pass is more expensive than the forward pass. So let's go take a closer look at this forward pass function, which I conveniently already decorated with a profile. And you see that 83% of that time is spent in the fetching a single batch. So what's going on in that function? It's calling get dataset every single step, which is reloading the dataset and then forming a batch from that. So, okay, this is a bit, of an artificial situation. You would never want to put this, but it could happen to anyone when you're, writing these things quickly. And you don't want to have the get dataset called every time step. So we are going to extract that, load it once at the top of the file, and then just form batches from this global variable. I've already done that in the IOFix version, which I've already spoiled and showed everyone how fast it was. But in case you missed it, we're almost 7,000 images a second. So what? That's a factor of 30x speed up. Not too bad for changing one function. You can look at the profiler output. I think I'm running short on time, so I'll let you look at it yourself, but you can see that there's still a lot of time spent in the forward pass relative to the backward pass, but it's much better than before, certainly. But we have a long ways to go to get to 1 million. So for that, we're going to want to go to our next folder, which is TF function. What I've done in this one, specifically this file, is again, I've added some decorators. This time, it's a TF function decorator. I've removed the profile ones from before so I've commented out a handful here because the one we care about most is this one that runs over this new function, which I've just carved out of the training loop, which is the train iteration of the forward pass and backward pass. Basically, what you saw was taking 95% of the time there. So what this does is, well, a bit of background. In TensorFlow 1, which was before there was eager execution in TensorFlow, you had to define the entire computational graph before you executed it. Now it's more like traditional Python you're used to, where things are run as soon as they're executed, more or less. So it's good for productivity and usability to have this eager mode that is now the dominant one in TensorFlow 2. But we lose some of the performance we might get with having the entire graph defined, because every time, let's go up to the call function, every time one of these lines runs and produces some output, it's usually shuffled around in memory and cached in memory because it doesn't know what you're going to do with the outputs from a single layer. Rather than just, it doesn't know that you're going to take an input and it's just going to flow through this computational graph without any need for the intermediate outputs. So one way to recover that and get some of the performance back is really simple, and that's just adding this decorator, which tells TensorFlow, take all these TensorFlow tensors and operations and layers and link them together and execute them in a single kind of kernel launch, or a graph launch specifically. So very trivial change. One thing you'll have to watch out for is if you have NumPy operations in here, they can't be translated into TensorFlow graph operations directly, so it'll be treated as a fixed quantity. So that's problematic if you're generating some random NumPy input, and it's then going to be fixed for all iterations or all invocations of this TF function. And there's some other pitfalls to watch out for. But this will recursively go through and turn everything it can into a single graph call. So let's see what we get with this. Oh, keep forgetting I'm not in the right place. Okay, so we're at 74,000 images a second, 10x plus speed up just from a single function decorator right there, which is pretty amazing. But we can do even better. Looking at the step time, those in the know with had experience with these GPUs, I think Weeho mentioned, once you get down into this type of execution time on a single GPU, there's not much more overhead. So one thing we can do to improve our throughput is to increase the amount of local work. Now, given MNIST digits are quite small and the network's quite shallow and not very wide, an easy way, configurable way to do this is to increase the batch size, which we have set to 64, I think, right now. Let's turn it up to 1024 because we love powers of 2. Wow. So here is, I will already tell you, the peak of what we're going to get for this tutorial. Over 1 million images a second, which is obscene. You do training extremely quickly with that. But in theory, there's ways you could make this even faster. Still, you see the step time, even though I, some crazy factor of 2 increased the batch size and the amount of local work for the GPU to compute per batch, the step time is still quite small. So that's already to tell you that we might be at our limit here for this particular problem. But one thing that will always be recommended in these tutorials is to then, once you have a TF function graph defined for your training loop, to perform XLA translation. So XLA is a linear algebra, accelerated linear algebra dialect that can further improve on these graph definitions by fusing short operations together, such as convolution followed by an activation function. It can do that once rather than swapping the outputs again into memory. Specifically, the memory constraints on a GPU mean that this is often an easy way to get more speed up. So without changing anything, you can even just enable XLA by taking the same command and prefixing it with this option, this TensorFlow option, which does this clustering procedure, which takes a look at your graphs that you've defined through TF function, and it performs just-in-time compiling to figure out whether or not this would be valuable for performance-wise. So let's try it out. So it actually got slower by like 20%. We're down to 860,000 images a second. I will note that this is a different lesson than the one I saw when I adapted this from an earlier tutorial that examined this profiling with a generative adversarial network, which was slightly more complicated, but still a small network, where XLA actually gave a 10% boost. So it's always important to tailor your performance lessons and approaches to increasing performance to the size of your problem and the specifics of your workload. In fact, even in the earlier, I tried this out with the June container of TensorFlow that was distributed by NVIDIA, and it actually crashed when I tried to enable XLA. XLA is a few years old now, so it's pretty stable, but this is where you're getting on the bleeding edge of performance and things can break or things can get slower, not as simple as turning on a function and it will always get faster. You can also enable force, actually, XLA compilation specifically within the file rather than globally trying to have it auto detect things by adding an option to the function decorators. So I think I've done it here just as an example. You can play around with adding XLA to different subsets of these calls. So actually this is wrong. It should be experimental underscore compile equals true is a way to force XLA compilation of that graph. Okay, I'm running short on time, so for the last 5 minutes, I'm just going to discuss reduced precision. I'll skip over the TF profiler, which is a valuable way to get a deeper look at the functions that are being executed on the CPU and the GPU. I encourage you to test that out, and you can really play around with it a lot on your local machine once you generate one of these profiles. So reduced precision is very popular these days, especially with the latest generation of GPU that we have on Theta GPU. This is because there are special functional units on the GPU, called tensor cores, which you probably heard about earlier, that can do FP16 and mixed FP32, FP16 calculations extremely quickly. Enabling mixed precision in TensorFlow is, in theory, quite easy. It can be as simple as one line, which I'll jump to right here, which is to set the global policy, which I have set it to standard single precision float 32, and all you have to do is change this to mixed float 32 or float 16, which should automatically take all your Keras functions and take the ones that are safe for turning to half precision and perform that automatically for you. But also, you might need to do something called loss scaling, which then scales, as it sounds like, scales your loss function output so that you don't run into floating point artifacts when you're computing these tiny losses under flow specifically. So let's see how we do with reduced precision. So surprisingly, it's extremely slow. Oh, I think this is with the small batch size. But skipping to the punchline, it is still a bit slower. And I think at this point, once you look at the profiler that I've included in that other folder, which I skipped over, you'll see that we're basically at the limit here for the device and how fast we can compute these things. And we're latency bound by the kernel launch execution time. So what I would encourage you to try is to make these layers and the overall network a bit fatter so there's more work for the GPU to do, and then try again adding mixed precision and see if it changes the outcome. Again, both mixed precision and XLA had beneficial impacts for the GAN example, which I've linked to in the tutorial. So that's one way you can compare and contrast a simple CNN and a GAN performing the same steps, and you get very different results in very different performance and lessons. Here, I could just try this. Okay, that somehow got, oh, that's a bit faster than the last one, but still much slower than before. Then finally, I'll just leave you as I take a question or two. I've taken screenshots of the TensorFlow built-in profiler that I ran on the non-mixed precision case. You can ask questions about this and how you can see into, before mixed precision was enabled, it knows that 100% of the total device time was spent on single precision computation. You can see here the initial steps of your training loop are slow as TF function, graph compilation, and other heuristic algorithm and setup initialization costs occur. But then once you get to every other epoch or every other step in epoch, it's minuscule. And that's how we're kind of at the speed of light for the device for this particular workload. We have breakdowns of the various kernels and the time spent there on the GPU. And you get this nice timeline you can pull up where here all like 99% of the steps all occur in these very small kernels right here. And then here's the initial graph compilation and setup over the first 10 steps or so. I think I'm out of time, so I'll take any questions. I can answer more in Slack or via email since I had to rush through things.
Thanks, Kyle.
We're a little behind schedule, so do you want to take